about him. So next slide, sir. So Dr. Toyoshi Minami is an associate professor. He belongs to the Department of Materials and Environmental Science, Institute of Industrial Science. He's also a part of the Department of Chemistry and Biotechnology, Graduate School of Engineering. Also a part of Department of Advanced Interdisciplinary Studies, Graduate School of Engineering from the University of Tokyo. He has several awards and achievements to his credit. A few of them are mentioned here. The Japanese Photochemistry Association Award for a Young Scientist in the year 2020. SHGSC Japan Award of Excellence in the year 2020. Encouragement of Research in Polymer Science, Young Researcher Award of the Electrochemical Society of Japan, Young Innovator Award on Chemistry and Micro Nano Systems, the Chemical Society of Japan Award for Young Scientists, Young Chemists, etc. So his publications has achieved an H-index of 27 with a citation number of 1633. So his areas of research are supramolecular analytical chemistry, self-assembled materials, gold nanoparticles, and organic transistors for sensing applications. So with this very brief introduction, I now invite Professor Toyoshi Minami to continue with this lecture. Thank you, sir.
Yes, sir. Professor, you can carry on now. I can stop sharing.
Oh, okay. Can I share? Okay.
Yes, sir. Yes.
Yes.
Okay. Okay. Thank you very much for your kind introduction. I'm very happy to have the opportunity to talk about our current research in here. So I'd like to share my screen now. So please wait a moment, please. Wait. Can I see my screen?
Yes, sir. Yes, Professor.
Okay, so I'd like to start my presentation. So my research background is supramolecular chemistry. Especially, I'm trying to develop the chemical sensors based on especially the organic transistors. Then I'd like to briefly talk about my current research topics. So here is the contents. The first is the introduction of the organic thin-film transistor-based chemical sensors, and also the three types of the latest topics I would like to show. First is a molecularly imprinting polymer-based organic sensor, and the second one is microfluidic system attached to organic TFT, and also the last one is a bit different topic, the water-gated organic TFT transistors. Okay, I'd like to show that one. First, that is the background of the organic TFT. So as you might know, the organic transistors have three electrodes, so source, drain, and gate electrodes. The organic semiconductive layer made of the organic materials such as pi conjugate polymer or small molecules. So, and when we apply the gate voltage here, so we can manipulate the current between source and drain in here. So this is a typical relationship between the gate voltage and drain current. As you can see, when we don't apply the gate voltage, we can just see the noise. While after we apply the gate voltage, we start to observe the amplification of the drain current. So this is on state and this is off state. That's a 0 and 1 signal we can obtain. That means electronic engineers can use such device for the switching device. Thus, many electronic engineers try to use such device for the flexible electronics, especially for the display and so on, because the transistor can fabricate electronic circuits. While I'm a chemist, thus I thought we can use such device for the chemical sensors. So here is the reasons. So organic thin-film transistors have several advantages. For example, so sensor and transducer and data processing system could be on the one chip in the near future. And also organic TFT devices can be fabricated using printing technology. I'm not electronic engineer. However, I know how to use printers, for example, inkjet printer and so on. That is relatively easy to fabricate device. Thus, I decided to use such device for the chemical sensing platform. So how can we use the organic transistor as a chemical sensors? So several device structure can be employed. The first one here is like the semiconductive layer we can use for the detection portion, or gate directed layer we can use for the detection portion. So this is like the simplest device, while the OSC, organic semiconductive layer, is not so stable against water. Thus, for the first trial, we decided to fabricate the extended gate type transistor. In this case, the extended gate electrode is partially extended. Here is the detection portion. In that case, the water is completely separated from the organic semiconductive device. So that means we can obtain a relatively stable signal. So that's I decided to fabricate such device as a first trial. So how can we detect target molecules, biomolecule or environment protons through the organic transistor? Here is a mechanism. The surface of the extended gate electrode is functionalized with artificial receptor or immunoproteins. In that case, the self-assembly monolayer we employ for the fabrication of the receptor. In that case, the receptor can be fixed on the extended gate. If target analyzed, the plus or minus charged molecule is bound on the surface of extended gate electrode through the molecular interactions, we can see the changes of the surface potential of the extended gate electrode. Thus, finally, we could see the such like electrical property change, such threshold voltage change or drain current change. Here is a very simple mechanism. How can we detect the molecules? If like the, for example, minus charge compound bound on the extended gate electrode, so Q, that is like charge molecule affect on the threshold voltage. That means here is a voltage. Why can we see such changes? Because as you might learn at the high school, so the Q equals CV, that is the voltage and the Q, the charge and the capacitor related with this equation. That's if the Q is changed, the threshold voltage should be changed. Based on such simple theory, we could detect target molecule. Actually, to be honest, not complicated, but we can detect such molecule based on such phenomena. So based on such phenomena, I try to detect target molecule. From here, so one by one, so three types of sensors I like to show. First one is a molecular imprinted polymer functionalized organic TFT. So MIP is called as plastic antibody. That is based on the polymer synthesis. We can make a kind of like highly selected artificial antibody. So in this case, the yellow circle one, that is a target molecule. That is a component of the monomer unit, and it can bind to the target molecule. If we mix the target molecule and also the such a component, before the polymerization, we can make such like the complex. After we fully polymerize, we can remove the target molecule. That's the kind of like after we remove template, such like hole exists in the polymer. So such like the hole, we can use selective detection of target molecule as a sensor unit. So thus I decided to functionalize such MIP on the extended gate electrode. Then as a target molecule, we decided to taurin as an example. Then such like electrical property change of the organic TFT, we observe it. So here is the taurin, the target molecule. It's a kind of like nutrient, and also we need taurin for like general life. That's in the, for example, kids' milk or the like energy drinks, the taurin contains. So such because of the such importance in our body, I decided to get taurin. So here is a typical design of the organic transistor. So the other semiconductive layer, we employ the PBTTT, kind of like polymer, high conjugate polymer, because we can use the solution processes to fabricate semiconductive layer, and relatively we can reproduce response and the data. And on the other hand, extended gate electrode is functional with a polymer unit. So the polymer components I selected is like the 1,2-diamino-benzene and dopamine. So in this case, before we fabricate the MIP, we designed based on the wave function calculation and DFT calculation. So the calculations predicted that So the components ratio should be the dopamine, and 1 to diamino-benzene and taurine should be the 3 to 1 to 1. So it's in this ratio we can obtain the complex complementary complex such like that. So based on such calculation, we mix these components and polymerize based on the electrochemical method. After we polymerize the compound, as you can see, the cyclic bolt diagram showed almost all like very significant changes. So this one, we could say that we functionalize the MIP on the exchange gate electrode. Actually, we have like such data based on the AFM and so on. But today I have no time to explain detail, but we already characterize the electrode by using the microscope and also electrochemical measurement system. After this period, so we decide to detect the taurine. So this is a typical example of the transistor characteristics, the gate voltage and drain current. As you can see, when we increase the concentration of the taurine, so we can see the shift of the transistor characteristics. So here is like the relationship between the taurine and also threshold voltage changes. We clearly see nice saturation curve, and the lower end of the concentration is a linear line. So also the selectivity is important. So that case, taurine shows the highest response through the very similar like the other components. So that means this is not from the physical absorption. We can detect it through the MIP's selectivity. And also this is a washable and also the reusable. After we immerse in the taurine solution, then we extract it through the hydrochloric acid and deionized water. Then, so this pore can be regenerated, and then such like even though repeat several times, still we can get the target molecules. The final approach, so also we detected the taurine in the food. So that means we also detected the taurine in the real samples too. So this is the first example, the MIP functionalized organic transistor-based sensing. Okay, this is the MIP sensing. So next is a microfluidic system. The microfluidic system is very helpful to monitor the target molecule in a real-time manner. Thus, we decide to like combine the microfluidic system to our organic transistor system. As an example, we decide to use an artificial receptor that is a phenylboric acid to detect the glucose. So phenylboric acid, as you might know, can coordinate with the glucose through the dynamic covalent bonding. So even though glucose is the non-charged compound, when they make a boronate ester, minus charge on the boron unit can be shown. Just such minus charge unit can be detected by the organic transistor. And also the microfluidic system, also we functionize on the gate electrode. Then, so first try to realize the microfluidic system attached same gate type organic transistor for the glucose detection. So here is the design. So as I said, we also use a PVTT unit for the semiconductor layer. And also to decrease the operation voltage, also we employ the gate directed material, tetraidesphosphonic acid. Because this is a very thick molecular level, very thin material that we can higher the dielectric values. So we can decrease the gate voltage. And also the surface of the gold electrode functionalizes with phenylboric acid. On those microfluidic chamber system we put on the gate electrode. The width and height roughly 50 micron and 100 micron. The flow rate is 25 microliter per minute. This is because we want to monitor the activity of the cell reversal in the future. Okay, so this is the design of the microfluidic system. We also designed by using the COMSOL software. That is the commercial available software to design the microfluidic system. So here is inlet and here is outlet. So this is a simulation of the solution. How can the solution spread in the chamber? So red is like water. As you can see, the red solution is homogeneously spread in the chamber. That is important to continuously monitor target molecules. After we simulated such like the device, we fabricated such like microfluidic chamber. based on the PDMS pattern manufacturing system, as you can see like that. So then after we fabricated device, in this case, we could see that we injected the glucose and try to wash up by using the phosphate buster solution. After we inject the glucose, immediately the drain current change, we observe it. But after we wash by using phosphate buffer, immediately also the base go back to the baseline. So this is repeatable. That means our organic transistor functional with microfluidic system continuously could monitor glucose. And also the such like changes of drain current totally depend on the concentration glucose. When gradually decrease the glucose concentration, the drain current change completely depend on the glucose concentration like that. So continuous and gradual change, we can observe it. And also gradual increase of the glucose, we observe also too. And random injection, because the cell activity is quite sometimes random, that's even the random injection of glucose, we could continuously monitor the concentration. So now we are trying to monitor the activity of the liver cell. So hopefully we can report in the near future. So that also this is a kind of like thin gate electrode, but also we try to make a very thin film. So on the 1 microfilm, so we fabricated the organic transistor for the immunosensing. So to fabricate such device, I decided to use a dual gate type organic transistor. So this is like the actual device structure. In this case, gate electrode is on the top, and then so we can sweep the bottom gate voltage. So this is a stable operation, and also we can functionize a top gate electrode with a receptor and printing technology. As I said, inkjet printer we can use to fabricate device. Thus, we try to detect the dual gate type organic transistor. So the immunosensing, we achieve it. So that means like regularly, if you want to detect protein, enzyme linked immunosolvent assay is required. So that means several proteins and also enzyme and fluorophore, chromophore, we need to target one protein. So in this case, it is a very like accurate. However, the problem is a bit like complicated procedure we have to employ, because as you can see, several protein, enzyme, and also dye we have to use in the one assay. So that is not relatively easy to achieve it. So that's level-free detection of the as a target model. So mouse IgZ, we tried because as you know, IgZ now is a kind of a marker for the COVID-19 too. So that is a very helpful to detect if we can detect IgZ, so immunoglobulin Z. So in this case, top gate electrode we functionalize with anti-mouse IgZ from the gut. So through the immunointeraction, we can detect the target IgZ, even though without any labeling on the target mouse IgZ. So this is actually a fabricated device on the 1 micrometers thick, very thick film. So this is a very thin, as you can see, that means we could make a wearable biosensor. That is, we believe so. So the top gate electrode is functional with biosyn, because the biosyn can make an interaction with strophtavidin to fix the anti-mouse IgG. So that is, and also here is a reference electrode. Here is the detection portion. This is a transistor unit. So I do not explain too much detail, but this is a component of the fabricating the device. So this is a silicon material, and also like the organic material to employ to fabricate such device through the inkjet printing. And first, this device is very, very thin. Thus, we have to check the mechanical like strength. So we bend it and compress. So that case, even though we bend or compress the such device, almost all the transistor characteristics does not change. That means even though such device, even the compressor bending, like that, in that case, still has like the organic transistor properties still survive. So almost no change. So then we try to detect such device. Based on such device, we detected the mouse IgG. So here is the relationship concentration of the IgG and also shift of the threshold voltage. As you can see, depending on the concentration of the IgG, we clearly see the change of the threshold voltage. So that is like a very thin, I guess, most thin device over the world for the immunoassay. So we believe that that is we can fabricate a wearable immunoassay device in the near future.
Sir, sorry to interrupt you. You have 5 minutes time.
Okay, so I'll finish my 5 minutes. So lastly, we fabricated the exchange gate electrode basically, but last time I would like to show the kind of like the semiconductive layer we can use for the sensing portion. So polymer, so in that case, polymer layer, we use all the sensing device. So pi conjugate polymer, we can use two methods for the sensing application. That is optical sensing and also electrical sensing, as I showed here. So the pi conjugate polymer can show the fluorescence. That's also, in our group, also fabricate optical sensing system based on the pi conjugate molecules. So polymer, in the case of polymer, we can achieve more sensitive detection in comparison with a small molecule-based sensor because amplification in the polymer chain, we can observe it. So however, I thought which method is better to develop a sensor because like the one material can use for optical sensing and electrical sensing. I thought which is more better or not. Thus, I try to compare such sensing ability. So to compare such device, I decided to fabricate water-gated organic transistor. So that case is we use water as a gate dielectric material. So that case, electric double-layer capacitor we can use for the gate dielectric. So minus or plus charge compound make a very thin the ionic membrane on the semiconductor layer and gate electrode. Thus, we could decrease the operation voltage because, as you know, the capacitor value completely depend on the thickness of the gate dielectric. So we previously achieved 0.3 volt application for the organic transistor. So that is a very low voltage we can use for the sensing application. So I thought in this case, the if we function an actual receptor on as a side chain of the polysilicon unit, so such receptor can capture target molecule through the molecular interaction. Thus, we could see such the change of the organic transistor property I thought that. So as a target molecule, we selected the glyphosate, that kind of herbicide, so that can kill the weed. But that compound now it's a big problem because like the IRC is classified glyphosate is probably carcinogenic to human, and especially European countries now in the California states to start to quit such like herbicide. Thus, the detection of the glyphosate is important, while current method is just only GC mass spec. That means in the agricultural field, we cannot measure it. Thus, we try to develop the simpler chemical sensing system. So here is the design of the water gate transistor for the glyphosate detection. So carboxylate attached polysilicon unit can make a kappa ion complex. So such complex can detect the glyphosate. This is a mechanism. So that when first the kappa complex with the carboxylate, while glyphosate can strongly coordinate with the kappa ion. Thus, in this case, the charge of the kappa ion state can be changed on the surface of the semiconductor layer. I thought we can see such changes based on the equilibrium. So here is the fabrication process. So side gate structure we employed. That is a very simple way. Even the part-time job person can fabricate device. So we just drop the water and then try to measure the target, try to measure electrical properties. So here is a scheme. The addition of target and pipetting water and electrical measurement. And this we repeat this cycle. Here is the transistor characteristics. So 0.3 volt operation voltage. So we achieved very low operation voltage, and it's not almost strong hysteresis. So that we can use for the such sensing device application. So when we increase the glyphosate concentration after the complex between the polysilicon and also the kappa ion, So when we increase concentration, glyphosate gradual change of transfer property, we observe it. So that case, we could clearly see the detection of the glyphosate. So here the concentration change the drain current. If we do not add copper ion, almost no change, we observe it. So that means such like the copper ion equilibrium is important to the target molecules. So selectivity is quite nice. Glyphosate is the highest response. We achieve it. And finally, we try to compare such like detection ability with fluorescence sensing. So in this case, to detect the on-site detection, we fabricate the glass chip. So that case, we mix the polymer with the hydrogel and on the glass tip, and we take a photograph of this fluorescence image, and we analyze such detection limit. So here is the result. So when we employ the fluorescence detection, in that case, limit of detection 0.95 ppm, while our like organic transistor shows 0.26 ppm. Even though we employ the same material, they show the different LOD. So this case is the organic transistor is more sensitive way to detect glyphosate. So this is the first example when we compare the first example, the comparison between the fluorescence and the organic transistor, which is more suitable device which platform the chemical sensing application. Okay, anyway, so I need to summarize my talk. So when we mix a molecular chemistry, a microfluidic system, and also organic device, we can create new research field that we can contribute to develop the inexpensive and flexible chemical sensor device in the near future. So finally, I'd like to thank to my lab members. So several, like for example, DDA is a fabricated microfluidic system, and Dr. Minamiki and Dr. Sasaki fabricate organic transistors. And I'd like to say thanks to the financial support. Thank you very much for your kind attention.
Thank you, Professor. We are now open for questions. Any questions from the audience?
Yeah. Yes, Professor. I had one question.
Yes,
Yes.
Yeah. You have said that the polymer can be extracted. What is the type of method that you can use to extract the polymer from the
polymer?
the first part of the top?
MIP. Okay.
Yeah.
MIP.
Yes.
Okay. So what is the question, please? Sorry,
Yeah. That's the previous slides.
Previous slide.
Yeah.
This one.
Yes. So you said the extraction of polymerization. How can you do that? The extraction.
Electrical polymerization. Okay. So that case is okay. This case is we use the kind of like diol compound, also like amino compound. It can make oxidation. So when they make oxidation, it could be polymerized. Make sense? So that is, for example, this is cyclic voltammogram. So when we apply the potential, so first we can see such like the electroactive compound because the such like component exists. After we oxidize the such like components, it starts to be reactive. Then we cannot see almost like this cyclic voltammogram. This is the results.
Okay. And one more thing, the extended gate electrode. What is the dimensions that dimensions of? Yeah.
Roughly like so we can change the size. In this case, for example, the size here, I can show the photograph here, roughly like 15 millimeter, roughly here.
Okay. Okay. Thank you, Professor.
Professor, I have a question.
Yes, please.
Could you think of any biomedical applications for this microfluidic device that is developed by you?
Yes. Actually, yes. Thank you for your nice question. So today I do not explain too much details, but originally, so that is we use for the liver cell activity because as you know, the glucose metabolized by the liver cell. So that's I'm contacting with a kind of medical doctor to monitor the liver cell activity. So I incubate the actual cell, the liver cell, and also like try to attach the microfluidic system. Then we try to monitor such like glucose metabolism. in our body, in the human body's activity like this.
Thank you, Professor. So, any other questions from the audience? You can post your questions in the chat box, please.
No, ma'am. There's no question.
Okay.
Yeah.
Okay. So I think we can wind up this talk.
Yeah. Professor,
so
you can stop sharing. Professor, you can stop sharing.
Okay.
Yeah. Thank you.
So thank you, Professor, for that enlightening lecture on the applications of various organic transducers. Especially you had emphasized in the field of microfluidic device and chemical sensing systems. So thanks for joining us, sir.
Thank you very much.
So we now move on to the next lecture of the series, invited lecture 4 by Professor Naoki Wakia. So his topic of presentation is preparation and property of thin film gas sensors for combustive gases. So he is from the Shishoku University, Japan. So I now take this opportunity to introduce him to the audience. So Dr. Naoki Wakia is a professor in the Faculty of Engineering, Department of Electronics and Material Science, Graduate School of Science and Technology, Shishoku University, Japan. So a few of his awards and achievements. He has this Japan Society for the Promotion of Science. He has also got an award for the Ceramic Society of Japan. And he's also the editor-in-chief of Distinguished Reviewer in 2014, and he has an H index of 23. His research interests are manufacture of thin films of oxide ceramics, magnetic materials, dielectrics, ion conductors, etc., using the dynamic error PLD method, in which an electromagnet is introduced into the vacuum chamber of the PLD device, self-assembled microstructures, thin films, and ceramics. I now invite Professor Naoki Wakia to deliver his lecture.
Thank you, Chairman. Thank you, Professor. Can I share?
Yes, sir. Yes, Professor. Yes. You can share your screen.
Can you see?
Yes, Professor, we can see.
Okay. So, okay. Thank you for giving us to give this good opportunity to make a presentation in the ICONN 2021. So, the title of my presentation is Preparation and Property of Thin Film Gas Sensor for Combustive Gases. So, just a moment.
Professor, sorry to interrupt you. Your presentation is 25 minutes.
Okay.
Yeah, 5 minutes for the question and answer sections.
Thank you.
Yeah, thank you, Professor.
So, semiconductor gas sensors have been investigated intensively to detect reducing gas such as LPG and CO and CH4 and ethanol and H2S and hydrogen and chloride and some volatile organic compound VOCs. And the principle of semiconductor gas sensor is like this. In air, this is for the case of the N-type semiconductor, the surface is oxygen is absorbed on the surface of the particles or surfaces. Then depletion layer is here. Just a moment. So depletion layer is here. So there is a high potential barrier. So the electrical conductivity is low. However, if reducing gas is given, then adsorbed oxygen is removed, and the thickness of depletion layer is become thin, so the potential barrier is lowered, and the electrical conductivity increases. And so this is the principle of the conductive gas sensor for the conductive reducing gases. And the materials for the reducing gas sensor is there are many materials. For example, the first gas sensor is reported using the zinc oxide and indium 203 and SnO2 thin dioxide. However, an important difficulty associated with this material is low selectivity. Selectivity means distinguish one target reducing gas from other interfering reducing gas is difficult. So spinel ferrite with general formula AB204 are promising for use as gas sensor material because they show more selectivity than the metal oxides, single metal oxide like SnO2 or zinc oxide, because we can choose some selection the A and B element. And so ferrites ferrites are reported to show the sensor response, such as zinc ferrite, nickel ferrite, copper ferrite, cadmium ferrite, and cobalt ferrite, and magnesium ferrite. And so from the as a form of the gas sensors, sintered pellets and thick films, and thick film is synthesized using coating a paste of, made of the nano-sized particles and thin films. And in the case of nano-sized particles, the specific surface area is large. And in the case of thin film, usually specific surface area is small. So, but not so much, large number of report about thin film. So we'd like to propose a new method to get high specific surface area to obtain high surface response, and a new principle to obtain the high sensor response. And this is our future strategy. As I told you, that the demerit of this semiconductive gas sensor is low selectivity. So so thin film array. So we'd like to use this kind of thin film array, compose different materials having different sensor response, will improve the selectivity and target reducing gas from other interfering reducing gas. And the purpose of this work is we have two purposes, and one is to develop deposition deposition of zinc ferrite thin film on porous silicon. This is the purpose for the part one. And the purpose for the part two is a spontaneously formed superlattice structures of neodymium ferrite thin film. So at first, I'd like to make presentation about the part one. So deposition of zinc ferrite thin film on porous silicon substrate. So at first, I'd like to explain the concept of this part. So this is a thin film on silicon substrate, and this is a porous silicon. And if we deposit thin film on this substrate, as this is a schematic image of nucleation and growth of thin film silicon and porous silicon. On silicon, this is a nuclei, and there's a low nuclei density, and so it will grow like this. So large grain size is realized. So it means a small specific surface area. But if we use porous silicon as a substrate, since there is porous structures, so many nuclei will be formed. So high nuclear density is expected. And since the then and grain growth is limited, so the grain size is expected to be small. So a large specific surface area is expected. So we think that this using porous silicon as a substrate, a large sensor response will be realized. And this is an explanation for the zinc ferrite. So zinc ferrite gas sensor is it shows excellent sensor response for LPGs. This is the composition dependence of the gas sensor response with a zinc ferrite, and this black is a zinc ferrite, and this blue is a nickel ferrite, and this red is nickel zinc ferrite. So this data means that the selectivity peak point of the selectivity can be changed by changing the composition, the nickel zinc ferrite. And in this case, zinc ferrite, the maximum sensor response is reported to be 74%. And this is a porous silicon. The porous silicon is formed by anodic oxidation of silicon in HF ethanol mix solvent using this kind of anodic oxidation. And so the purpose of this part one is to prepare zinc ferrite thin film on silicon and porous silicon substrate using pulsed laser deposition. And second, to examine surface sensor response of zinc ferrite thin film on silicon and porous silicon using pulsed laser deposition to evaluate the ability of porous silicon as a substrate for the sensors. And this is the experimental, that is a preparation of porous silicon. The porous silicon is synthesized using this anodic oxidation using these conditions. And we use a high doped N-type silicon substrate as a silicon. And as a result, this is a SEM image of the surface of the porous silicon. And the oxidation time is 300 seconds. It is only 5 minutes. But using this anodic oxidation, the 46 nanometer porous silicon layer is obtained. And if we enlarge this area, so we can see this cylindrical and vertical nanopores is obtained. And the average pore diameter is around 13 nanometers. And percentage of holes, it means this percentage of the surface holes is around 18%, and hole depth is 46 micrometers. So porous silicon having cylindrical vertical nanopore structure is obtained. And this is on this porous silicon, we deposit zinc ferrite thin film using pulsed laser deposition. And after that, the sensor property is measured using laboratory made gas sensor apparatus like this. In this case, we measure the sensor response for the LPGs and CO gas. And this is a gas sensor property measurement procedures. So first it's air, then LPG or CO gas is introduced, then evacuate and air is introduced again. So this is a XRD pattern of zinc ferrite thin film deposited on silicon A, silicon, and B, the porous silicon. So zinc ferrite thin film is polycrystalline, having 1-1-1 preferential orientation for the silicon substrate. But on porous silicon, the preferential orientation is not so strong. So this change of the orientation is considered to be brought about by the change of the microstructures. So we observe the microstructures. uh, in the case of the thin film, this is a surface of the, zinc film deposit on porous silicon and the cross-section image. And this is a zinc thin film, the surface image on silicon. Sorry, this is on silicon. On silicon, this is on cross-section on silicon. So the grain size, average grain size of the thin film deposit on porous silicon is small, as 45 nanometers. But the zinc ferrite deposit on silicon, not porous silicon, is large and around 120 nanometers. And from the cross section, we can see that on the porous silicon, the surface is rough, and in the case of silicon, the smooth surface is obtained like this. And this is a sensor. This is a sensor properties for against LPGs. This is a A is for the zinc ferrite thin film on silicon substrate, and B, this one is a zinc ferrite thin film on porous silicon. After introducing LPG gas measured at 375 degrees C, and the resistance of the zinc ferrite porous silicon thin film is at least one order higher than that of zinc ferrite on silicon substrate. This suggests that grain boundary is responsible for the potential barrier, and this is a sensor response. A sensor response is defined using this equation, and RA is a resistance in air, and RG is a resistance in the gas. So this graph shows that steep initial rise is observed on the for the zinc ferrite film deposit on porous silicon substrate, and sensor response is almost higher. Sensor response for the zinc ferrite thin film deposit on the porous silicon is higher than that deposit on silicon substrate. And since there is some change of slope, we analyzed the change of this one. Change of the conductance with time is obtained like this. And this slide shows that the slope change here. So this, but this is a change of temperature. It means the temperature is constant. So this slope change is not derived by the temperature change during measurement. So using this analysis, we can obtain just a possible explanation for the two energetically different absorption state. This is change maybe obtained from the different. There are two different absorption sites, or macropores and mesopores, and different state of oxygen. It means molecular oxygen O2 or atomic oxygen O is responsible for the change of this slope change. Anyway, zinc ferrite shows this kind of properties, and this is a change of the response, sensor response with temperatures. So this slide shows that this is a reported value, and our data is here. So on the porous silicon and on silicon. So this result shows that the PLD prepared zinc ferrite thin film deposit on porous silicon shows a high maximum sensor response. Although the temperature of the maximum sensor response is rather high. But we'd like to say that this steep slope shows that this thin film shows a high selectivity for the LPG at these temperatures. And in the case for the CO gas, this is a zinc ferrite serum and on porous silicon. Zinc ferrite thin film on porous silicon shows a high sensor response and quick response. And this is all. This is a temperature dependence of sensor response. So this slide shows zinc ferrite thin film deposit porous silicon thin film shows a faster and higher sensor response than zinc ferrite silicon thin film. This is a summary of the part one. So the PLD prepared zinc ferrite thin film on porous silicon shows high maximum sensor response. Although the temperature of the maximum is high, temperature dependence of zinc ferrite thin film prepared using PLD shows a steep initial rise. And for the CO gas, the sensor response of zinc ferrite deposit porous silicon shows faster and higher sensor response than the film on silicon substrate. So this means that porous silicon is a good platform to prepare reducing gas sensors. This is part one. And this is part two, the new concept.
Professor, sorry to interrupt. You have 5 minutes time.
Oh, okay. Sorry, this is part two is a new type of the sensor. So in this case, we'd like to use there one report that artificial superlattice gas sensor shows a high gas sensor property and a quick response. So and we have reported a new technique that we can realize spontaneous superlattice formation by just applying magnetic field during deposition for the strontium titanate thin film. So we'd like to apply this technique for the neodymium ferrite. Sorry, we don't have enough time, so I skip this one. And the nickel neodymium ferrite is with purpose structure is reported to show this kind of sensor response. And this material is orthorhombic perovskite structures. So, sorry, I don't have enough time. So the purpose is to realize new sensor material. And okay, I'd like to skip this one. And so this is sensor data. The thin film deposit without superlattice structure show this kind of sensor response. And the neodymium ferrite thin film having spontaneous formed superlattice structures, the thin film shows a higher sensor response. So summary of the part two, the spontaneous superlattice formation is observed for the neodymium ferrite having neodymium-rich composition. So neodymium O2 is, I'd like to skip this one. And so the neodymium ferrite thin film with spontaneously formed superlattice shows higher sensor response than that without superlattice. So dynamic oral PLD, our method, is promising as a novel method to realize fast and high sensor response at the same time. So this is a conclusion. We propose novel two methods to obtain high sensor response. One is to use porous silicon as a substrate, and second is to use the technique to obtain the spontaneous formed superlattice structures using dynamic oral PLD is effective. Okay, so we'd like to apply this method to realize a VOC sensor like this. So use many materials. Okay, thank you very much.
Any questions from the audience?
Yes, Professor, there is a question.
Yes.
Is it possible to do retweet refinement analysis for the zinc ferrite to find the structural characteristics? There's a
Mr.
question from audience.
Okay.
Yeah, zinc ferrite.
Correct, this one.
Yeah.
So, you mean the experimental condition?
No, they are asking about, is it possible to do retweet refinement XRD? Retweet refinement XRD.
You mean read better analysis?
Yes.
Okay. This is a thin film sample. So, read better analysis is for the powder sample.
Yeah, that is
So,
the question is that possible? Can we do the retweet refinement for zinc ferrite?
I think that it is very difficult to
Hmm.
carry out read better analysis for thin film because there is a preferential orientation.
Okay.
So I have a question, Professor. So in the last slide, you had mentioned an application for breast cancer. Is it
Yes.
possible to extend to other types of cancers also? The last slide.
So since
Yes,
okay.
patients of breast cancer. Is it possible to extend to other types of cancers also?
Yes. Okay. It is reported that
Okay.
VOC of the patient is included in the aspirated air in the patient. So
Yes.
the composition and the uh, component of the VOCs depend on each cancer. For example, breast cancer and lung cancer is
Yes.
famous for to detect and for the cancer. This is used diagnostic.
Okay.
So this sensor uh, measurement using this kind of array sensor will be helpful to find out cancers without suffering from some other measurement.
Okay. Okay. Thank you, Professor. Any other questions from the audience?
Thank
So
you,
any
Professor. On behalf of
okay.
organizing committee and SRM IST, thank you for your acceptance and give a nice presentation.
Sorry, I missed it by the time.
Thank you, Professor, on behalf of organizing committee ICON and SRM Institute of Science and Technology.
Thank you very much.
We have a good lecture that we had, and we are accepting for our invitation. Thank you once again.
Thank you very much.
Thank you, Professor. We thank you for sharing your extensive research knowledge in the area of porous silicon and its comparison with other materials. It was a very enlightening topic. Thank you, Professor.
Thank you very much.
Ma'am?
Yes, sir. Shall we
I
now
can
move
share.
on to the contributed lecture session, sir?
Yes, ma'am. Yes, ma'am. I can share them.
Okay.
So you can
Okay.
call the name. They are in the already in the talk. They are already attended. So
Okay,
they
sir.
already enter into the talk. So I can share them.
I have the list with me, sir.
Yeah. You can just
I
read them,
can.
ma'am. Yes,
Yes,
ma'am.
yes. So I now call upon Pooja Shukla for the contributed lecture on the topic of preparation of PVDF matrix encapsulated with quasi 2D graphene nanoflakes for optoelectronic devices. Pooja Shukla is available.
Pooja Shukla, are you here? Pooja Shukla.
available, sir?
I think so, ma'am. If she is here, then she can. Pooja Shukla, are you here? Pooja. Okay, let us see,
I
ma'am.
think you have to unmute them.
No, even not in. Even I cannot find her name actually.
Dr. P. Bobo, I'm able to see. Okay, that is somebody else.
Dr. Pooja Munjal is there,
Okay.
not Pooja Shukla. I think we can move on to the. I don't know whether if he is here, I think we can ask them to present.
Okay.
Participant.
So if Pooja Shukla is not available, I now call upon P. Harisha to present the paper titled Negative Schottky Barrier Height and Surface Inhomogeneity in N-silicon MIS Structures. Harisha, you can share your PPT now.
Can't hear you, Harisha. Harisha, you hear us? We can see your presentation. Do you hear us, Harisha?
Yeah, I'm here, sir. Am I audible?
Yes, yes. Now we are audible.
Yes. Can you
so
see?
Yes, we can see. We can see the presentation. So
okay.
Only 10 minutes time.
Yeah.
So within that 8 minutes presentation, 2 minutes questions.
Okay, thank you.
Yeah. You carry on.
Okay.
Mr. Harisha, please go to the full slide mode.
Yeah.
Yes.
Okay. Thank you, Madam Sir. Very good afternoon, everyone. My name is Harisha CP, a lecturer in Government Polytechnic, Harapanalli. And today I'll be presenting my research work that I have conducted during my master studies at National Taiwan University, Taiwan. The topic of my lecture is negative Schottky barrier height and surface inhomogeneity in N-type silicon MIS structure. I have done this research work under the guidance of Dr. Siddharth Joshi, Professor NIE Mysore, Dr. Minghan Liao, Professor NTU Taiwan, and Dr. Chi Chung Kai, Division Director, National Applied Research Laboratories, Taiwan Republic. So I am going to discuss some literature survey, then the objective and methodologies that I have adopted here, and the atomic layer deposition and its application here, and the electrical properties and the extraction of Schottky barrier height and the experimental analysis, followed by the conclusion. So the one of the biggest problem that the complementary metal oxide semiconductor industry is facing, the contact resistance at the source and drain in field effect transistor is the biggest issue. This contact resistance at the source and drain is probably one of the reason behind this contact resistance is Fermi level pinning at the metal semiconductor interface, and this is due to the metal induced gap states or bond polarization. So to reduce this contact resistance, we need to deepen the Fermi level pinning, and this can be effectively done by introducing an ultra thin dielectric layer in between the metal and semiconductor. And this insertion of dielectric layer is going to deepen the Fermi level pinning. And in this present research work, we have used two very effective and very popular dielectrics. One is titanium dioxide and hafnium dioxide. And we have also, extended the research work to study the inhomogeneity in Schottky and ohmic contacts. As I said earlier, in the conventional metal semiconductor contact structure, the problem which we are facing is the thermionic barrier in between the metal and semiconductor. This higher Schottky barrier height is reducing the transport phenomena and thereby biggest issue in the CMOS industry. So by inserting, on the other hand, by inserting a thin dielectric layer in between the metal and semiconductor, we can reduce the thermionic barrier. That means we are going to reduce the Schottky barrier height. But one thing is very important at this stage is the thickness of the thin dielectric layer is very, very important, because the thickness should not be too high. If the thickness of the intermediate layer is too high, means it's going to produce tunneling barrier. So our experimentation has conducted with 1 nanometer, 2 nanometer, and 3 nanometer titanium oxide and hafnium oxide, and also with bilayer structure. So what we have done is, we have taken an N-type silicon with phosphorus doped. What we have done before actual experimentation is, we have cleaned the surface with acetone, alcohol, and DI water, and the native oxide has been removed by DHF cleaning, diluted hydrochloric acid cleaning, followed by DI. So the one of the novel method to produce nano thin layers is atomic layer deposition. So we have done atomic layer deposition for titanium oxide using two precursors. One is TD mat and H2O. TD mat is nothing but tetrakis dimethyl amino titanium, and another precursor is H2O under controlled environment. And hafnium oxide has been by inserting a thin dielectric layer is, so you can see the first curve is, the black curve is platinum N-type silicon. This is a MS structure. MS means a metal semiconductor structure, where you can see an asymmetric nature. That means there is a higher forward current and lower reverse current. This shows that there is a Schottky barrier in between the metal and semiconductor. By inserting the thin layers of titanium oxide of 3 nanometer, 2 nanometer, and 1 nanometer, and also a bilayer of one is TiO2 1 nanometer, another one is HFO2 of 1 nanometer. We have observed that there is an increase in reverse current. The reverse current improvement shows that there is a reduction in the Schottky barrier, right? And at the same time, there is a slight increase in the forward current also. This may be because of the lower band energy of the inserted dielectric, which reduces the series resistance. And with respect to hafnium oxide also, we have seen the improvement in the reverse current. This clearly shows the reduction in Schottky barrier height. For the extraction of Schottky barrier height, we have used a JV model at room temperature, which considers forward bias. But considering forward bias will not fetch you the accurate result, because it will not take the Richardson constant into consideration. By considering the uncertainty of Richardson constant and effective diode area, we have used a thermionic emission model to extract the Schottky barrier height, where the IV curves will be done at different temperature levels. And in our research work, we have done IV characterization at 5 different temperatures, starting from 298 Kelvin to 378 Kelvin with the 20-degree intermediate states. So we have observed that in the conventional Richardson plot, in the curve you can see here, it gives you a non-linear behavior, both in terms of MS contact as well as MIS constant contact structure. Here also, in terms of MS and MIS contact structure, we have observed a non-linear behavior. And after the extraction of Schottky barrier height using this plot, we have observed that the Schottky barrier height for MS contact was 0.53 electron volt, and with the 3 nanometer TiO2, the Schottky barrier height was minus 0.058. This means the Schottky barrier height has been decreased to a negative value. And you can see that the bilayer structure of 1 nanometer TiO2 and 1 nanometer hafnium oxide also resulted in negative Schottky barrier height. So there is if you compare this Schottky barrier height values, there is an increase in 122% reduction in Schottky barrier height with respect to bilayer structure, and there is a 112% reduction in Schottky barrier height with respect to insertion of 3 nanometer TiO2. So this is what our experimental observation. And in summary, in the graph we can see here the MS contact structure. The traditional MS contact structure, the thickness was around 0.54, and with the bilayer structure of 1 nanometer TiO2 and 1 nanometer HFO2, the value is minus 0.12. There is a drastic reduction in the Schottky barrier, right, with the usage of bilayer as well as 3 nanometers of TiO2. So it is proved that the insertion of 3 nanometer TiO2 has effectively reduced the Schottky barrier height as well as the bilayer structure. In our research work, we have also extended the research work to understand the surface inhomogeneity between metal and semiconductor, in between the metal, insulator and semiconductor structures. We have used a Gaussian distribution model, a very popular model to study the surface inhomogeneity. And by using this, we have what we have done is we have calculated a apparent Schottky barrier height with respect to different temperatures. And here is the curves we have seen here. And using these curves, we have calculated the apparent Schottky barrier height at 5 different temperatures. And we have drawn the modified Richardson plot. So in the thermionic emission model, we have seen a conventional Richardson plot. Here in Gaussian distribution model, we have seen a modified Richardson plot. This is a linear graph you can see here, but the conventional Richardson plots have shown non-linear behavior. So this clearly indicates that there is a inhomogeneity. What is the other confirmation for non-linear behavior? Inhomogeneity is as the temperature increases from 298 to 378, there is also an increase in Schottky barrier height in all the models, in all the contact structure. There is an increase in Schottky barrier height. You can see here for MS contact, the Schottky barrier height got increased from 0.6 to 0.88. Here 0.6 to 0.8. There is an increase in Schottky barrier height with respect to temperature, and there is a decrease in ideality factor with respect to increase in temperature. So this is the confirmation of a surface inhomogeneity in both MS structure as well as MIS structure. And there is also one more comparison is from the conventional Richardson plot and modified Richardson plot, we have calculated the Richardson constant. In case of conventional Richardson constant, the value of Richardson constant is very, very low. This is supposed to be 112 ampere per centimeter square Kelvin square for N-type silicon, but the conventional Richardson constant is very, very low. And in case of modified Richardson constant from the plot, we have seen a very close value. And there is also a standard deviation with respect to the Schottky barrier height at various temperatures. This has clearly shown that there is an inhomogeneity in both the MS structure as well as MIS structure. And the Schottky barrier height maybe is not because of the surface inhomogeneity. It could be because of some other reason which requires further investigation. So conclusion, we found that the MIS structure can have reduced Schottky barrier height and thus can yield lower contact resistance at source and drain region compared to MS contact structure for N-type silicon. TiO2 in its monolayer form was much effective than hafnium oxide for platinum on N-type silicon. The interfacial dielectric in its bilayer form proved to be more effective than monolayer. So one of the positive point in our research work is we have investigated the bilayer structure, insertion of bilayer, that is 1 nanometer hafnium oxide, 1 nanometer TiO2 oxide has proved 122% reduction in Schottky barrier height. So also we have done a theoretical study using Gaussian distribution model for both MS and MIS structure. We have seen that there is inhomogeneity in both MS contacts as well as MIS contacts. So these are some of the references, and thank you.
So any questions from the audience, please?
Any questions?
Yes.
Yeah.
Yeah. See, if there is no much effect about inhomogeneity, then what is the purpose that you are saying about inhomogeneity here? Your presentations, from your presentation, I understand that by just introducing the dielectric layer into the semiconductor pin structure, so there is a reduction in barrier height. So, and you said that it is not due to the inhomogeneity of the material. Then there is no need to discuss about inhomogeneity in your presentation right now.
Yes. So earlier research works have shown that inhomogeneity could be one of the reasons for Schottky barrier height. But the fundamental purpose of keeping a thin dielectric layer is the thin dielectric layer between the metal and semiconductor is going to passivate the surface. So the passivation effect is the biggest factor which will reduce the Schottky barrier height. But the inhomogeneity will be there. It is obvious in both the metal, MS contacts as well as MIS contacts.
Yeah. So can you tell me what do you mean by inhomogeneity? I understand different way, and what is your meaning? Can you tell me?
Inhomogeneity is in the context structure. In the context structure between metal and semiconductor. So here there is a area, contact area.
That
There
is
is
what
a
the interface between the two
where
materials. Yes.
yeah, where some points will have lower Schottky barrier height and some points will have higher Schottky barrier height. So the current transport mechanism through different points will be different. So the overall
can it due to the composition in the material?
yes,
If there is
yes.
any changes in the composition of the material.
That is also one of the reason people have observed. For that reason only, we have used a very novel technique called atomic layer deposition. Atomic layer deposition is a very a novel technique which will give you a very uniform layer. And from composition point of view also, it is highly proved technique. So the inhomogeneity may be because of dipole moments at the interface, intrinsic and extrinsic dipole moments.
You are muted. Harish, you are muted.
Yes, sir.
Yeah.
Audible now?
Okay. Yeah. I understand. Thank you. Thank you for a nice presentation.
Yeah. Thank you.
Yeah.
Thank you to SRM. For
there is
this.
any questions, you can put in the chat box. Okay, there are no more questions. Thank you once again.
Thank you so much.
Yeah,
sir.
you can stop sharing your screen.
Thank you.
Thank you, Mr. Harisha.
Thank you, madam.
I now call upon the next presenter, M. Thirumalai, to present his paper, Mesoporous Silica Monolith Based Colorimetric Probes for CO2 plus ions.
Hello, ma'am. Hello.
Yes.
Yes, sir.
Sir, am I audible?
Yeah,
yes,
you are audible.
Sir.
Okay, sir. Can I start now?
Yes, please go to the full screen mode.
Good afternoon, everyone. First of all, I like to thank ICONN-2021 for considering my research work in a oral presentation mode. I'm M. Thirumalai, doing PhD under the guidance of Dr. M. Akila Mageshwari. My research work title is Mesoporous Silica-based Colorimetric Probes for Cobalt-2 plus ions. Usually, the cobalt metal ions is highly essential nutrient in human being, but when the limit is exceeded 0.05 milligram per liter, it may promote various kinds of health issues. So we have developed a solid-state colorimetric sensor to detect cobalt metal ion. These are the major methodology involved in our work. First step, we have prepared mesoporous silica monolithic material and chromoionophoric probe. Followed by we have fabricated the probe onto the silica monolithic template. Then steps involves the we are after fabrication we also investigate the properties of before and after fabrication of probe onto the monolithic material. Finally, we optimize all the analytical parameters to develop a cobalt sensor. Synthesis of mesoporous silica monolithic material, we have used a solid template method. We have taken a P123 as surfactant aerating agent and TABB as a swelling agent. TOS we have taken as a silica precursor. Under proper aging and the calcination conditions, we have obtained silica mesoporous silica monolithic material. These are general procedure, general mechanism involved in the preparation of silica monolithic material, a surfactant forming a micelle at a critical micellar concentration. When we are adding a inorganic silica precursor under aging and hydrothermal and concentration process, we have obtained with mesostructure material. After template elimination, we have obtained hexagonally arranged material. In HRSMMUs, the silica monolithic material confirms the presence of macroporous network with mesoporous channels. And then in HRTMUs, it's confirmed the presence of hexagonal honeycomb structure network in the material. Also, in effective studies, confirm the displacing value of silica monolithic material. In SAD pattern, it confirms the materials are in amorphous nature. Also, in ADAX, it confirms the purity of the material.
We have prepared TDQ probe ligand that's reacting in between two amino acids with 8-hydroxyquinoline. We also confirm the complex ability of the ligand using JAWS plot and BH plot. In JAWS plot, it confirms that it's forming a 1:1 ratio of complex, and also in BH plot, that's the binding constant. In liquid state, it's showing a 5.6 into 10 power 3 molar inverse. Also in solid state, it's showing that 2.5 into 10 power 5 molar inverse. These are best indication the probe has a stronger affinity in solid state medium. After that, we have fabricated the probe onto the silica monolithic material by direct immobilization method. We also investigate the properties of material before and after fabrication. In BET image, it shows that there is a decrease in the surface area, also decrease in the pore volume. So it indicates that the probe molecule uh, uh, probe molecule is highly arranged in a silica monolithic material. Also in XRD, in wide angle XRD, it shows that both the materials before and after fabrication, it's showing a amorphous nature. Also in wide angle XRD path, it confirms that there is no any damage in the material. It's showing a original position. After that, we have prepared Gopal complex to know the oxidation state of a Gopal. It confirms that it is in a Gopal 2 plus oxidation state. Also, we have confirmed all the element present in the materials. After confirming all the material characterization, we also optimized the analytical parameter to develop a Gopal sensor. In pH studies, the material showing the highest intensity signal response at pH 7 with a probe concentration of 0.05 millimole with a 4 gram of material. Also, we investigate the properties of material through in a kinetic response. It's showing within 3 minutes of time. After that, we also investigate the influence of other cations and the anions. We found that the material showing a excellent activity towards directing Gopal 2 plus ion with apparent color response. After that, we also investigated a concentration of metal ion by taking various concentration. As you can see here, from 0 ppb to 200 ppb, it's showing a color change from light orange to dark brownish color, which confirms that even very low concentration we can treat the metal ion. Also, we have calculated the limit of reduction, limit of quantification for this material by plotting a concentration graph, and the LOD is 0.12 ppb and the LOQ is 0.41 ppb. These are the limit of other cations and the anions that we have optimized. Also, the sensor material suggested that still 7 recycle we can use without any damage in the original performance. Also, we have investigated the LOD, LOQ.
Tirumala, you have 2 minutes time.
Oh, okay, sir. Also, we have compared with the other already reported material. We found that our material is showing a superior in the reduction limit. Summary of the work: we have successfully synthesized chromoinophoric ligand, which can provide an excellent selective response to a Gopal metal ion alone. Also, we have fabricated the chromoinophoric ligand onto the mesoporous silica monolithic material by direct emulsion method. The developed material showing an excellent colorimetric response even at very low concentration by showing a limit reduction of 0.12 ppb. Thank you for your attention. Hello, sir.
Yes, yeah. Now the section is open for discussion. If there is any questions, you can put in the chat box. So if there are no more questions, so we thank the speaker. Professor?
Yes, sir. So by any chance, Pooja Shukla is back?
I don't know. I will just let search in the once again. I think we don't need to wait, I guess, because
Okay,
it's
sir.
their headache.
Okay, okay. I don't
Pooja Shukla is not there yet.
Not that. That's what I'm also searching.
Yeah.
Okay. Okay, sir. In that
Thank
case, I
you.
think
Thank
we
you.
can close the session.
Yeah,
I'll
yes,
now
yes.
hand over to Professor Ganesh.
Thank you, Professor Jayanti. Thank you for sharing the section and accepting our invitation on behalf of ICON Organizing Committee. We are very much thankful to you.
Thank you, sir.
Thank you, Professor.
Thank you, sir.
Yeah, I think we can leave the section.
Okay, sir. Thank you.